The Mechanics of Soap. What I'm reading here is from this Molecules book written by a Theodore Gray. You get that? Alright. Well, anyways, in here there are a lot of molecular compounds that are, diagrammed out. Check it out. These are the esters. See that? Pretty cool. Now, this book is very important because it goes over a lot of different types of molecules that we use on a daily basis, such as soap, polyethylene, ores, opiums, different types of drugs, wool of rock, different types of fibers, siphenics, gemstones, rocks, minerals, all that good stuff. Here's what chemical is this? Stevia. Okay, there's stevia. Check it out, right where my thumb is. Stevia. Big ass molecule. Serious. But one thing I wanted to point out specifically was soap. Now, soap is organized like this. There's a long chain of material of carbon and hydrogen, and then it has a polar head of, sodium, oxygen that sit right on the edge, just like that. So it's a long chain. Now, what you can do with soap is organize water from organic molecules. In other words, the polar head of the soap molecule is attracted to water molecules, which are also polar. The soap is the long ones, which organize all of it into the center, where the organic molecules are, and then the water stays on the outside. Now, that specific picture, I was like, wow, that looks like the phospholipid bilayer of, a simple little organism. Probably very early in the history of the evolution of life on the earth. And, flip 2 pages, and here we are. This guy was thinking exactly what I was thinking, or I was thinking what he was thinking, or whatever. But here's the little passage I want to read to you guys. It says, Soap and the Origin of Life. It's on page 67. When soap breaks up oil, it does so by forming microscopic spheres of oil completely surrounded by a wall of soap molecules, all with their nonpolar tails pointing in and their polar heads pointing out, because the water is what makes that happen. And the nonpolar are comfortable sitting in the center where the organic molecules are. It says here, that's a pretty interesting structure. A spherical object with an interior filled with organic molecules that are protected by a wall of robust soap molecules. It sounds a lot like a biological cell. In fact, there are reasons to believe that exactly this kind of soap sphere played an important role in concentrating and protecting organic molecules during the long phase of chemical evolution that came before recognizable life emerged. In any case, it's pretty intriguing that if you simply throw a random collection of organic molecules, entirely nonpolar, some of them, some partially polar, into a pool of water, they will spontaneously self-assemble into structures that facilitate interaction between the organic molecules. So in other words, the soap molecules, or any type of molecule that has a polar and a nonpolar head, will organize itself spontaneously, meaning it can trap the organic molecules in the center, which then interact with each other over long periods of time, and then form different kinds of molecules in there when they interact with each other. So depending on what gets trapped in the center will mix up and do a whole bunch of crazy stuff inside of it. In other words, not only is soap fundamental in allowing modern humans to continue the process of natural selection, I don't know about all that, it may also have played a crucial role in getting the whole thing started in the first place. So there we have it, people. a reasonable explanation for how life started. Polar and nonpolar molecules organizing organics from water. That's it. And then we have to explain different types of interior molecules, organic style molecules that would have been trapped inside inside those spheres, and then see what kind of chemical reactions would take place between those. And then we have the beginnings of life. Alright, today is May 19th, 2015.